Come on, my dears. Now we go for question number 27. Electric dipole placed in non-uniform electric field. How is the behavior of electric dipole when it is subjected to non-uniform electric field? Let us see. In textbook they have written that initially in this case there are force and torque both are exerted on the dipole. Resultant force is also exerted and resultant torque is also exerted. So not only dipole rotates but it also displaces linearly, okay. But then they have written that torque becomes 0. After some time, after traveling some distance, torque becomes 0 and still there is resultant force exerted on the dipole, so dipole continues to move linearly. But how this thing happens, they have not explained. I would like to explain this whole thing using one good figure. Just try to concentrate on the board, okay. Consider non-uniform electric field. Here is a positive point charge whose electric field is away from it, correct? And I say this electric field is non-uniform. What is non-uniform? See, if it is uniform electric field, then field vectors have to be parallel. Na? And here these field vectors are not parallel. If these field vectors are not parallel, meaning thereby this electric field is not uniform, it is non-uniform, okay. Now consider an electric dipole placed initially at this very position, making angle theta with this electric field, okay. This electric field is in this direction, okay, fine. Now tell me what will happen, because vector P makes some angle theta with vector E. At present this theta is neither 0 degree nor 180 degree, so there is some torque exerted on this dipole, correct? And under the influence of the torque, this dipole will rotate this way. When theta decreases and finally after some time theta will become 0. When theta becomes 0, then torque will become 0, correct? Fine. Now tell me, what about resultant force? On this negative charge, there is a force of attraction provided by this positive charge this way, correct? And on this positive charge, there is a force of repulsion provided in this direction. And this repulsive force is less because this distance is more. Here strength of electric field is less. Here this attractive force is more because this distance is less and hence strength of electric field here it is more. Because of greater or intense electric field here, there is a greater attractive force, and because of weaker electric field here, there is a smaller repulsive force. Ultimately, some resultant force is exerted on this dipole towards this charge, and so it continues to move in the direction towards this charge, okay. I mean to say, initially resultant force is there, resultant torque is also there. So initially resultant force is there, so dipole will continue to move linearly, and at the same time it continues to rotate because there is some resultant torque. But finally what happens, when this dipole rotates this way, finally when theta becomes 0, torque becomes 0. When torque becomes 0, after that this does not rotate. But when torque becomes 0, at that time this dipole gets aligned parallel to this electric field. Look, when theta is 0, vector P and vector E, both of them are in the same direction. Now on this negative charge, there is a force of attraction which is greater. On this positive charge, there is a force of repulsion which is smaller. So in this condition also, there is some resultant force exerted on this dipole towards this charge, correct? And because there is some resultant force towards this charge, this dipole will still continue to move in this direction. In this direction means in a direction or towards a region of greater intensity of electric field. As you move closer and closer to this charge, naturally strength of electric field will increase, okay. So remember, behavior of electric dipole in non-uniform electric field is such that initially there is some resultant force, there is some resultant torque, but after some time the resultant torque becomes 0. then after it stops rotating, but still there is a resultant force, and so in the direction of resultant force it will continue to move towards a region of greater intensity. Okay, fine. Now we go for question number 28. Attraction of small piece of paper towards electrified comb passed through dry hair. See, it is our experience that if you pass comb, say plastic comb, through dry hair, correct? When you try to comb your hair with a plastic comb, and if the hair is dry, then there is a friction between hair and comb, and in this process of friction, it so happens that plastic comb gets electrified, becomes charged, and it is now possessing some negative charge. In this process of friction, plastic comb receives extra number of electrons, so it becomes negatively charged. Fine. And here I have shown certain teeth of that plastic comb. Say this is plastic comb and these are some teeth of that comb. Just concentrate on this particular tooth. This is particular tooth, and as I said, this plastic comb is now negatively charged up. So I am showing some minus signs here just to indicate the presence of negative charge. Fine. Now for a negative charge, you know its electric field is towards it. So I must show field vectors towards this negative charge. Correct? Tell me, is this field uniform or non-uniform? It is non-uniform because these field vectors are not mutually parallel. But why they are not mutually parallel? Because as you come down this way, you can see the surface area decreases. Surface area decreases. And when surface area decreases, remember what happens? Surface charge density increases. In the bottommost end, here surface charge density is maximum. Naturally, when there is a presence of maximum amount of electric charge at the bottommost point, naturally intensity of electric field at this very tip would be maximum. So here intensity of electric field is maximum, and as you go this way or this way, intensity of electric field decreases. Okay? So here electric field is non-uniform. Fine. Now in that non-uniform electric field, I just place some piece of paper. That piece of paper is electrically neutral. But now what happens? Because of presence of this negative charge, electrons in this piece of paper are getting repelled this way. And when they are repelled this way, this part of the paper would lose the electrons, so it becomes positively charged up, and this lower part of the paper would receive extra number of electrons, will become negatively charged up. Correct? Now you can think of a pair of two charges having equal magnitude, opposite polarity, so it induces some electric dipole. Remind well, this dipole was not existing right from beginning. No, when you place this piece of paper in the non-uniform electric field, then after it is getting generated, so we call it induced electric dipole. Induced electric dipole. And from negative charge to positive charge, this is nothing but, come on, induced electric dipole moment shown by symbol vector P. Now in this case, what did you understand here? In the presence of non-uniform electric field, the dipole moves in a direction of greater intensity of electric field. So now tell me, this dipole will move towards this part because this part is having greater intensity of electric field. Still, if you have not understood, then I can show you. This distance is less, okay, compared to this distance. Now when this distance is less, when this charge is closer to this charge, naturally force of attraction will be greater, and here this negatively charged tooth will repel this negative charge, but the repulsive force will be less because distance is more. So I mean to say, on this side of the piece of paper there is a greater attractive force, on this side there is a smaller repulsive force. So ultimately resultant force will be in the form of attraction this way. This way means this direction is pointing towards this tooth. Ultimately this piece of paper is driven towards the comb, and when this piece of paper is going towards this comb, you can say there is some attraction. Okay, this is how the small pieces of paper, when subjected to this non-uniform electric field existing nearby, existing surrounding to this electrified comb, will move towards the comb. Correct? Means they are attracted. They are attracted. So when you have small pieces of paper placed in a region surrounding to electrified comb this way, those pieces of paper get attracted towards the comb this way. Got it? Fine. Come on, my dears. Let us proceed further in chapter number 1. Last time we had completed up to question number 28. Now let us begin with question number 29. Distribution of point charges. In practice, we have mainly two types of distribution of point charges. Which two types? I am showing you the classification. One is known as non-continuous distribution. Another is known as continuous distribution. If in a given distribution of point charges, the point charges are far away from each other, they are quite separate from each other, then it is called non-continuous distribution. Correct? But if point charges are spaced very closely, if point charges are located very closely, then that sort of distribution is called continuous distribution of point charges. Got it? Fine. Now this continuous distribution of point charges is further classified into three subcategories. First is linear distribution, second is surface distribution, third is volume distribution. Let us see all these three types of continuous distributions one by one. Okay. First of all, let us see about linear charge distribution. Correct? What do you mean by linear charge distribution? If point charges are located closely on a certain curve, then it is called linear charge distribution. If point charges are located very closely on a certain curve, then it is called linear charge distribution. Okay, fine. Now, in this linear charge distribution, we would like to have measure of quantity of electric charge. Where quantity of electric charge is more, where quantity of electric charge is less, we would like to have some measure of it, and for that we have defined a special type of charge density called linear charge density. Linear charge density. Okay, fine. That linear charge density is shown by symbol lambda. Its formula is capital Q upon capital L, that is total charge upon total length. Total charge contained in a given linear charge distribution divided by total length of the curve along which the linear charge distribution is there. Okay? I mean to say lambda equals to Q upon L means total charge upon total length. Total charge contained in a given linear charge distribution divided by total length of that linear charge distribution. Okay? And now if you want to define lambda, how would you define it? Very simple. Charge per unit length in a linear charge distribution is called linear charge density. Linear charge density. Now on the linear charge distribution, if you just select a particular segment which is extremely small, then we call it length element, and its length I am taking by symbol dl. Correct? An amount of electric charge contained in that length element is supposed dq, which is very small. Correct? Here while taking the ratio, you may write any amount of charge in the numerator, but the condition is corresponding length you are supposed to write in the denominator, or reverse. You may write any length here in the denominator, but the condition is the amount of electric charge contained in that length you must write in the numerator. You must put up the values, respective values, okay? Don't put the values haphazardly. Now from this also you can define, in case of linear charge distribution, amount of electric charge per unit length is called linear charge density, shown by symbol lambda. What about its SI unit? SI unit of lambda is SI unit of charge divided by SI unit of length. For charge, everybody knows it is Coulomb. For length, come on, meter, correct? Coulomb upon meter, fine. What about dimensional formula for lambda? You must write dimensional formula for charge and length. Come on, for charge, have you remembered from 11th standard? A raised to 1, T raised to 1. A raised to 1, T raised to 1, correct? A for ampere, okay? T for time, remembered? And divided by length. Come on, for length, what is the dimensional formula? L raised to 1. So, I am writing here L raised to 1. Take it up in the numerator. So, it will become L raised to minus 1, A raised to 1, T raised to 1. Okay? L raised to minus 1, T raised to 1 into A raised to 1. Altogether, this becomes dimensional formula for linear charge density. L raised to minus 1, T raised to 1, A raised to 1. Got it? In a given linear charge distribution, if it is uniform, then value of lambda is same everywhere in all the length elements. But if given linear charge distribution is not uniform, then value of lambda is not same everywhere. Okay? My dears, here I would like to clarify one thing. In many books, it is so written that for non-uniform linear charge distribution, value of lambda is different at different points, correct? According to me, this sentence is not proper. You cannot say that value of lambda is different at different points, meaning thereby at each point value of lambda is likely to change. It is not possible. This is very wrong to say like this. I can make you convince with my argument. You know, suppose you have a class of say 50 students, correct? In your class, suppose there are 50 students. Now, can you say that all the 50 students have different heights? Can you say all the 50 students have different heights? You cannot say. You should say height of each student in my class is not same. That is proper sentence. You can say height in my class for each student is not same, but you cannot say that different students have got different heights. There may be possible out of 50 students, some 5 students may be like that, whose height if you measure even in millimeter also would come out same. So remember, you should not say that heights of different students are different. You should not say like that. You can say height of all the students is not same, correct? Similarly, if you have got non-uniform linear charge distribution, then you should not say that value of lambda is different at different points. Means at each point it will change. No, it's not possible. Better you say value of lambda is not same throughout. Okay, fine. Now we go for another type of distribution called surface charge distribution. In case of surface charge distribution, the point charges are located very closely on some surface. If point charges are located very closely on certain surface, then it is called surface charge distribution. Okay? Here, the density of charge is known as surface charge density. The way here it was known as linear charge density, here it is called surface charge density, shown by symbol sigma, correct? What was linear charge density? It was total charge upon total length. Here, total charge upon total surface area. Okay, fine. How would you define surface charge density from this formula? Very simple. In case of surface charge distribution, amount of electric charge per unit surface area is called surface charge density. I repeat, in case of surface charge distribution, the amount of electric charge per unit surface area is called surface charge density, shown by symbol sigma, correct? Now, in a given surface charge distribution, if you select very small segment, very small section, then that section is called surface element, or sometimes we call it area element, correct? Its area I am taking as dA, an amount of electric charge contained in that very small area is suppose dq, which is again very small, okay? Then this is the amount of electric charge contained in that very small area element, sometimes we call it charge of charge element, and this is area of area element, okay? From here also you can define, in a given surface charge distribution, amount of electric charge per unit surface area is called surface charge density, shown by symbol sigma, correct? What about SI unit of sigma? Very simple. For charge, it is Coulomb. For area, meter square. For area, meter square. So, what is the SI unit of surface charge density? Coulomb upon meter square. Here it was Coulomb upon meter. Here it is Coulomb upon meter square. What about dimensional formula? For charge, everybody knows A raised to 1, T raised to 1. For area, L raised to 2. L raised to 2. Just take it up, L raised to minus 2, T raised to 1, A raised to 1. L raised to minus 2, T raised to 1, A raised to 1. Got it? Fine. Here also, if given surface charge distribution is uniform, then value of sigma is same everywhere. But if given surface charge distribution is non-uniform, then value of sigma is not same everywhere. Okay, fine. Now we go for the last type of continuous charge distribution, that is volume charge distribution. Okay, if point charges are located very closely in some three-dimensional space, then it is called volume charge distribution. Volume charge distribution. Okay, here the respective charge density is known as volume charge density, and it is shown by symbol rho. Volume charge density shown by symbol rho. Here it is defined by this formula, total charge upon total volume. Here total charge upon total length, here total charge upon total area, and here total charge upon total volume. Come on, define it. In case of volume charge distribution, amount of electric charge per unit volume is called volume charge density, shown by symbol rho. Simple. Now, in the volume charge distribution, if you select extremely small volume, then we call it volume element, and that volume is shown by symbol dV, and amount of electric charge contained in that extremely small volume element is suppose dq. Okay, from here also you can define, come on, in case of volume charge distribution, amount of electric charge per unit volume is called volume charge density, shown by symbol rho. Simple. What about SI unit? SI unit of charge is Coulomb. For volume, you know it is length into breadth into height, meter into meter into meter, that is meter cube. Coulomb upon meter cube. What about dimensional formula? Come on, for charge, as usual, we have seen previously, A raised to 1, T raised to 1, A raised to 1, T raised to 1, correct? Divided by meter cube, that is L raised to 3. Its dimensional formula is L raised to 3. Just take it up, then it is L raised to minus 3, T raised to 1, A raised to 1. Okay, L raised to minus 3, T raised to 1, A raised to 1 is the dimensional formula for volume charge density. Okay, fine. Come on, we proceed further. Let us see now question number 30. It is about linear distribution of point charges. Just consider a linear charge distribution over this curve, correct? In this Cartesian coordinate system, we have shown certain linear charge distribution on this curve. Remember, it is simply not a geometrical curve, it is indicating linear charge distribution. So, you are supposed to show such dots which indicates the presence of very closely spaced point charges. Okay, fine. Now, in this theory, what we are supposed to find out? What is the resultant Coulombian force exerted by this entire linear charge distribution on a point charge located outside the distribution? What is that resultant Coulombian force? And then after we will also find out the resultant electric field produced by entire distribution at that very point. Okay? Let us find out both the things. First is resultant Coulombian force and then after electric field. Look. First of all, you just do one thing. This continuous linear charge distribution should be divided into extremely small length elements, each having length say dl dash. Okay? Where when we are using the symbol dl dash, remember from 11th standard, suppose you are writing dl, what does it mean? Limit delta L tends to 0. So, this is length of length element which is to be taken very small. Okay? Out of many length elements, as a specimen, I have shown one particular length element at this position. Okay, fine. Now, this length element should be chosen that small, such that it can be taken locally straight. Not only that, at least for that length, you can take linear charge density lambda as constant, correct? That sort of short length is known as length of length element. Okay, fine. Now, for this particular length element, its position vector with respect to origin is, suppose vector rj equals to vector r dash. Okay, fine. Now, we just select one point charge. Say ith charge. That is why the symbol is qi. Let it be equal to q. And for this ith point charge, its position vector with respect to origin is vector ri equals to vector r. Okay, fine. Now, in this length element, the quantity of electric charge is very small. We can take it almost as a point charge. Let it be jth charge. So, it is qj, and because quantity of electric charge is very small, we can show it by symbol dq, correct? Fine. Now, at this position, the value of linear charge density is suppose lambda, and if you just change the position, instead of selecting length element here, you may take it here, anywhere else. Then, if it is non-uniform linear charge distribution, then value of lambda will change, correct? That is why I am writing here mathematically lambda as a function of this position vector, which is vector r dash. Okay? If you change this position, then value of lambda may change. That is why mathematically you can say lambda is a function of vector r dash, correct? After all, tell me what is lambda? Linear charge density. And as I said, this length we have taken that short, such that at least for this length, we can take lambda as constant. And if you got linear charge density which is constant, what is it? charge divided by length. Charge contained in this length is dq, divided by its length we have taken dl dash. Okay, fine. Now tell me, what is dq from here? Transfer this. So dq would be lambda as a function of vector r dash into dl dash. Lambda as a function of vector r dash into dl dash. So dq is lambda as a function of vector r dash into dl dash. Okay, fine. Now recall the formula which we had studied earlier, vectorial form of Coulomb's law, vector Fij. What was that? Columbian force exerted on ith charge by jth charge. Columbian force exerted on ith charge by jth charge. What is Columbian force exerted on this ith charge by this jth charge? Come on, recall that vectorial form. Vector Fij equals to k qi qj upon mod of vector ri minus vector rj whole cube into vector ri minus vector rj. Come on, recall. Vector Fij, how much it was? Equal to k qi qj upon mod of vector ri minus vector rj whole cube into vector ri minus vector rj. Remember, I told to maintain the order. You can see the order is maintained. Ij, 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 Ij. Remembered? Fine. Now in this equation, I would like to make some changes at certain places regarding the notation, regarding the symbols. This force, if it is force exerted by this jth charge on this ith charge, then I would like to show it by this symbol, vector df, which is called partial Columbian force. Partial Columbian force. Why partial? Because at present we have considered only this much length, we have not considered entire charge distribution. Okay? Because we have considered right now part of the total linear charge distribution, then we call this force as partial Columbian force. Okay? To be shown by symbol vector df. This k as it is. What about qi? Qi is this point charge which is shown by symbol q. So qi is q. What about qj? Value of qj I already explained. It is lambda as a function of vector r dash into dl dash. Lambda as a function of vector r dash into dl dash. Correct? Divided by mod of vector ri equals to vector r minus vector rj is nothing but vector r dash whole cube. Vector ri is vector r minus vector rj is vector r dash. Correct? Fine. But I want resultant Columbian force exerted by entire charge distribution on this point charge. So in order to find out that resultant Columbian force, what you must do? You must make vector addition of all such partial Columbian forces exerted by each length element chosen continuously over this entire curve. And for finding that addition mathematically, what do we take? Integration, correct? But if that integration is taken over this curve, then it is called line integration. That's why I am putting the symbol L, correct? Here you must pronounce line integration of vector df. Line integration of vector df, correct? Now tell me, when you take line integration here, means you must take it here, correct? Because this is equal to this. When you take line integration here, means line integration here, at that time kq is constant, and when kq is constant, you can take it out of this symbol of integration, kq into integration of remaining part, lambda as a function of vector r dash into dl dash upon mod of vector r minus vector r dash whole cube into vector r minus vector r dash. Got it? So what does this give? This gives me resultant Columbian force exerted by entire given linear charge distribution on a point charge located outside that distribution. Got it? Now I want resultant electric field produced by this linear charge distribution at this very position. How would you find out? Very simple. Don't you know electric field is, from basic definition, it is resultant Columbian force per unit positive charge. And just to find out that, what you should do? You should find out vector F upon Q. You have vector F, you have Q here. Why do you take this Q in the denominator on left side? Yes, vector F upon Q. Vector F upon Q, if you find out from here, then it is K into integration of lambda as a function of vector R dash into dl dash upon mod of vector R minus vector R dash whole cube into vector R minus vector R dash. Correct? Tell me what is this? Resultant Columbian force per unit positive charge. What is it called? Electric field. You have found out this electric field, correct? But can you recall one fact? While finding electric field at a given point, you must place test charge at that very point, because while placing that test charge here, it will not produce any disturbance in this charge system, correct? So remember, if this is the electric field given by this formula, then in that formula this Q must be test charge. Remember the definition of test charge? A point like positive charge whose magnitude tends to 0 is called a test charge, correct? Fine. In the entire discussion, what is dq? It is charge of charge element. And what is dl dash? Length of length element. Length of length element. Okay, fine. Now we go for question number 31. Here in this question we have discussed about linear charge distribution. Now we go for surface distribution of point charges. If point charges are located very closely on some surface, then it is called surface charge distribution, correct? One such surface charge distribution is shown in the diagram on this surface. Fine. Simply it is not a surface, it contains point charges which are spaced very closely. That's why I am putting so many dots. Okay, fine. Now what we require to find out here? What is the resultant Columbian force exerted by this surface charge distribution on a point charge located outside the distribution? That resultant Columbian force we have to find out, and also electric field produced by this distribution at this very point. Okay, we will find out both the results. Look, first of all you do one thing, you just divide this entire surface area into extremely small sections. Each section is known as area element. Suppose area of area element is dA dash. Sometimes we call it surface element. Okay, either you say area element or surface element, one and same, and its area I am showing by symbol dA dash. Okay, fine. That area should be such small, it should be that small, such that the area element can be taken plane. Locally that area element should appear plane, and at least for that small area the surface charge density can be taken constant. That sort of small area is called area element. Okay, and one such area element I have shown in the diagram at this position, whose position vector with respect to origin is vector rj equals to vector r dash. Okay, fine. Now the charge contained in this extremely small area element can be taken as a point charge. Let it be jth charge. Okay, so I am showing by symbol qj, and because amount of charge contained in that area element is very small, I may show it by this symbol dq, which is called charge of charge element. Fine. Now when you are talking about surface charge density, it is to be shown by symbol sigma. If this distribution is non-uniform, then value of sigma is not same everywhere, correct? At this particular position, value of sigma is, suppose sigma as a function of vector r dash. Why do we write sigma as a function of vector r dash? Because if you just change the position of this area element, then this position vector will change. Depending upon that, in non-uniform charge distribution, value of sigma may differ. That's why I am putting mathematically this symbol sigma as a function of vector r dash, correct? And what is surface charge density? It is charge divided by area. Amount of electric charge contained in this area element is dq, divided by its area is dA dash. Find out dq from here, transfer this. Come on, dq will be sigma as a function of vector r dash into dA dash. Sigma as a function of vector r dash into dA dash, correct? Fine. Now outside this charge distribution, I just take a point charge, say qi equals to q, having position vector ri equals to vector r with respect to origin. Fine. Now what is Columbian force exerted on ith charge by jth charge? Columbian force exerted on ith charge by jth charge. Remembered earlier we had studied Columbian Coulomb's law in vectorial form. That vectorial form was this. What was that? Vector Fij equals to k qi qj upon mod of vector ri minus vector rj whole cube into vector ri minus vector rj. Come on, vector Fij equals to k qi qj upon mod of vector ri minus vector rj whole cube into vector ri minus vector rj. Throughout the equation, order is maintained. Ij, 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 ij. Correct? Fine. Now in place of this, I just write new symbol vector df. It is called partial Columbian force. Why partial? Because at present we have not considered the entire surface charge distribution. No, we have just considered very small part of it, and that's why this Columbian force is known as partial Columbian force. Okay, the small k as it is, instead of qi, what you can write? Q. Instead of qj, what you can write? Sigma as a function of vector r dash into dA dash. Sigma as a function of vector r dash into dA dash, correct? Divided by mod of vector r minus vector r dash whole cube. See, in place of vector ri, you must write vector r. Minus, in place of vector rj, you must write vector r dash whole cube. Come on, in place of vector ri, I should write vector r. Minus, in place of vector rj, I should write vector r dash, correct? Now we want resultant Columbian force exerted by entire surface charge distribution on this very point charge. And for finding that resultant Columbian force, now what you should do? You should find out vector addition of all such partial Columbian forces, correct? And that vector addition, mathematically you can write integration of vector df over entire surface. Because it is surface charge distribution, now you should go for surface integration. Earlier it was linear charge distribution, so we had taken line integration, correct? Now it is surface charge distribution, so we are going for surface integration, correct? And now when you take surface integration of vector df here, means you are taking surface integration over here, and when you take surface integration here, kq can be taken constant and out, okay? When k into q is constant, it can be taken out of the symbol of integration, and then inside it is surface integration of remaining part I have written as it is, okay? Fine. Now tell me, this gives me resultant Columbian force exerted by entire given surface charge distribution on a point charge located outside that distribution. Got it? Fine. Now we want electric field produced by this entire surface charge distribution at this very point. Then what you should do? How would you find out electric field? It is resultant Columbian force exerted per unit positive charge. All that you have to do now is to transfer this q in the denominator on left hand side. So you will get vector f upon q. And when you transfer q on the left side, left is on the right hand side, k into integration of sigma as a function of vector r dash into dA dash upon mod of vector r minus vector r dash whole cube into vector r minus vector r dash. Got it? Again, let me remind you, whenever you want to find out electric field at any point, which is normally called point of observation, at that very point you are supposed to place a test charge. So if you are finding electric field using this charge, then that charge must be test charge. A point like positive charge whose magnitude tends to 0 is known as test charge. Okay, fine. In the entire discussion, dq means charge of charge element. Charge of charge element. And what do you mean by dA dash? Area of area element. Area of area element. Correct? Area of area element. Got it? Fine. Now we go for question number 32. Look, first we had taken linear charge distribution, then we had taken surface charge distribution, and now in this question we are taking volume charge distribution. Volume charge distribution. Okay, fine. As shown in the diagram, you just consider some volume charge distribution contained in this volume. Okay, it is simply not volume, it is the volume occupied by very closely spaced point charges. That's why I am putting here dots. Correct? Fine. And such distribution you can just consider over the entire volume, inside the entire volume. Fine. Now, here what we have to do? We have to find out resultant Columbian force exerted by entire volume charge distribution on a point charge located outside that distribution. Okay, let us find out. First of all, do one thing. You just divide this entire volume into extremely small volume elements, each having volume say dV dash. Okay, and one such volume element I have shown in the diagram at this position. Okay, this volume of volume element should be chosen that small, such that volume charge density at least for that volume can be taken constant. Okay, and that constant volume charge density in this particular volume element I am taking by symbol rho as a function of vector r dash. Position vector of this volume element with respect to origin is vector rj equals to vector r dash. Okay, why I am writing here rho as a function of vector r dash? Because if this volume charge distribution is non-uniform, then value of volume charge density is not same everywhere. Okay, so if you just change the position of this volume element, then this position vector will change, depending upon that value of rho may change. Correct? Fine. Now what do you mean by volume charge density? It is charge divided by volume. Amount of electric charge contained in this volume element is suppose dq, divided by volume of this volume element is dV dash. Correct? Now charge contained in this extremely small volume element can be taken almost as a point charge. Let it be jth charge. Correct? Shown by symbol qj. And because quantity of electric charge is very small, I showed by symbol dq, which is charge of charge element. And find out dq now from here. Transfer this. So dq will be rho as a function of vector r dash into dV dash. Rho as a function of vector r dash into dV dash. Got it? Fine. Now outside this distribution, I have taken a point charge say qi equal to q, having position vector ri equals to vector r. Now what is Columbian force exerted by jth charge on ith charge? Remember vector form of Coulomb's law? It was this, vector Fij equals to k qi qj upon mod of vector ri minus vector rj whole cube into vector ri minus vector rj. Remembered? What is this? Columbian force exerted on ith charge by jth charge. Fine. Now at certain places I am making some changes in the notations. Instead of vector Fij, I just give a symbol vector df. You must have come to know what is vector df now. Partial Columbian force, because we have not taken entire volume charge distribution right now into consideration. We have taken only extremely small part of it. That's why we call it partial Columbian force. Correct? small k as it is. What about qi? It is q. Qi is q. What about qj? Qj is rho as a function of vector r dash into dv dash. Rho as a function of vector r dash into dv dash divided by, come on, mod of vector ri equals to vector r minus vector rj equals to vector r dash whole cube into vector ri equals to vector r minus vector rj equals to vector r dash. Fine. Now tell me, I want resultant Coulombian force exerted by entire volume charge distribution exerted on this very point charge. If I want resultant Coulombian force out of partial force, what you should do? You should go for taking integration, correct? But that integration is taken here over the inside this entire volume. That's why we call it volume integration. To be shown by this symbol, integration, and below that you must write V, correct? For linear charge distribution, you should go for line integration. For surface charge distribution, you should go for area integration or surface integration. And here we should go for volume integration. Okay, fine. Now, when you take volume integration of this partial Coulombian force, you are likely to get resultant Coulombian force exerted by entire volume charge distribution on this point charge, correct? Now, volume integration of this means volume integration of this, correct? But when you take volume integration here, k into q is constant, can be taken out of this symbol of integration, and inside this integration symbol, the remaining part I have written as it is, okay? This gives me resultant Coulombian force exerted by entire given volume charge distribution on a point charge located outside that distribution. Got it? Now, if you want electric field produced by this entire volume charge distribution at this very point, then just show it by symbol vector A. From the basic definition, what is it? Resultant Coulombian force exerted per unit positive charge. And for that, you should bring this q down. So it is giving you vector F upon q. Then left is k into integration of this remaining part over this entire volume. Correct? Fine. While finding electric field, you must have remembered at this point of observation, you must place test charge. So if you are finding this electric field using this sort of charge, it must be test charge, meaning thereby its magnitude should tend to 0. A point like positive charge whose magnitude tends to 0 is called a test charge. Got it? Fine. Throughout the discussion, dq means come on, charge of charge element, and dv dash means volume of volume element. Charge of charge element, volume of volume element. Got it?